because I'm just trying to wrap my mind around the stuff in chapter 14.
Okay.
So like if we could like if most of the class after you like kind of redefine everything, if we could we focus on chapter 14 and 15? Like that's where I
Sure,
got
sure, sure,
lost
sure,
with
sure, sure. Yeah.
groups.
I mean,
It's
if
just that
okay, good. All
conflict.
right. So let me just quickly say a couple of important things that I think I should get out about rings in general, and then I'll just see if all of you feel comfortable with the stuff in 12 and 13. Right? We can sort of spend our time in chapter 14. That's fine. That's no problem with that. There was maybe I think it's good to look at a couple of examples. So one of you for your DQ did the solving a quadratic using the quadratic formula, right? And that's kind of fun because it is a good way of thinking, but then it doesn't work all the time, right? And sort of looking at why it doesn't work gives some excellent examples of what you have to be a little bit careful of when you're working with just rings in general, right? So that's a thing to look at. Okay. Um, so let's do that. Maybe I can just make sure. Let me just look at the text myself. So I'm going to do this instead of looking at my notes because I just thought I'd change it up today a little bit. Definition of a ring. Anybody with problems just with the definition. It's got a plus. It's got a times. Does it always have a multiplicative identity? Right. Does not always have a multiplicative identity. The additive part is always a group, right? So you've studied groups to death, so you know when the additive part's a group. You've got the usual distributive laws, right? So there's nothing too strange about that. If it doesn't have an additive identity, it means it also doesn't need to have what? Like what kind
Uh,
of things? Yeah, go ahead.
Units? Oh,
It doesn't have to have units, it doesn't have to have inverses, right? To have an inverse, you have to have an identity, right? So if you don't have an identity, you can't even talk about an inverse. It doesn't even make sense, right? So that's a thing just to keep in mind, right? And Tringle, I'm sorry, you had your little hand up here.
Oh, I have a very specific question, but it's in chapter 14, so I'm going to wait till then.
Oh,
Just don't forget about me.
okay. Well, don't forget to speak up. Okay. Good. All right. Let's see. So there's a bunch of examples here. I think good examples, of course, are the integers, right? And for lots of what we're doing, you want to keep the integers in mind because as we go and start doing fields, which is sort of one of the major subgroups of rings, not a group in the technical sense, but subsets of rings. So those are the ones that behave the most like your number systems, right? You have inverses, you have units, all this sort of stuff works, right? But then we're going to add variables to the fields. So we'll look at polynomial rings over fields, right? And a lot of the properties they have will be similar to what the integers have, right? So you want to use the integers as kind of a basic set of examples for when you're thinking about, for example, rings of polynomials, right? So the sort of properties that integers have, rings of polynomials over a field will have, right? It's kind of like when you're doing vector spaces, right? You want to know about things like R2 and R3 and, sort of standard basic vector spaces, right? So Z and, ZNs and those things, those are going to be sort of your basic rings for lots of examples, right? Of course, other examples are the rational, any sort of numbers you teach kids, right? Rationals, reals, complex, all those sort of things, right? Okay. A really good example to keep in mind for avoiding, because you should have studied. I mean, I didn't teach your 512, so I can't know what you did in 512. But I know what you should have done in 512, and you should have learned things carefully, like matrix multiplication is not commutative, right? And that you can have a matrix A and B and multiply them together and get 0, even though neither of the matrices are 0, right? So you've got all these sort of things you have to be careful of. And matrices are a great example of all the sort of problematic things that can come up with rings, right? And it's also just a very important example, obviously, right? But the ring of matrices is what linear algebra is all about, more or less, right? Okay. And of course, matrices don't have, not every matrix has an inverse, right? So we were looking at the group of matrices earlier. We were looking at GLNR, right? Things like that. And there, all those matrices had inverses. So that was a group, right? But in general, you just take, n by n matrices over a field, right? And that forms a ring, right? You can add matrices, you can multiply them. You've got commutativity associated, you proved all that stuff in linear algebra, right? But you don't have inverses for all matrices, right? You don't have cancellation for matrices in general, right? So these sort of problems that come up with rings come up very naturally in matrices, right? And another example that you should keep in mind are functions, right? Like functions from R to R, or something like that, right? Functions under composition where you're adding coordinate-wise, right? That's kind of another very common example for a ring, right? So it's good just to have all those examples in mind, right? So that when you're working problems and you're answering a question about arbitrary rings, you don't accidentally use something very specific about the reals or something, right? You sort of have all these other examples in mind of how things can go wrong, right? Okay, does that make sense? Okay, first really simple thing your book has you show is that, additive identity is unique, right? We already knew that from groups. Additive inverses are unique. Multiplicative identity, if it exists, is unique. Same proof that we use for the groups, right? If an element has a multiplicative inverse, it's unique, right? Again, the same proof we used for groups works, right? So all those proofs are the same. Again, if you have any questions, I'm willing to do the proof. So ask if you have any. The one extra thing we get now is we get that 0 times something is 0, right? So that's something you can prove just using the other ring axioms, right? So that's something that follows. So it's worth doing those little proofs, not reading them, but just trying to do them yourself, right? So that's just the first couple of things in this chapter. What a subring is, right? Shouldn't be surprising. It's just a subset, which is a ring, right? And when you're going to check that something's a subring, you got to check that it's a subgroup. So the usual, how many things do you have to check for a subgroup?
Subtraction, and it will be under subtraction and multiplication.
So now the group is always additive. In rings, the group's always additive, right? So for the subgroup part, you have to check the additivity of the subset, closure under inverses, additive inverses, because that's all you have to be closed under, right? And the one other thing is you have to show that it's non-empty, right? So there's actually 3 things that you're supposed to check for subgroups, right? Non-empty, closure under multiplication, and closure under inverses, right? For subgroups, right? And the other thing you have to check for ring is just closure under multiplication. So you check that it's a subgroup and also closed under multiplication, and that's it, right? Okay. If you're trying to show that it's a subring with unit, then you have to do more. You have to show that it contains the 1, right? And if you're trying to show that it's a subfield or something like that, you'd have to show that it also contains inverses. Okay, so there are additional things you might have to check depending on what sort of substructure you're looking at, right? So that's one thing that changes. We get a whole bunch of different kinds of sub things now with rings. Because we'll have fields, we'll have integral domains, we'll have all sorts of stuff. Yeah. Sorry, Crystal, I can't hear you. I can see you talking, but I can't hear you. Still no sound.
That's writing and we're not able to see what you're writing.
I'm not writing anything. I'm just talking.
Oh, you're just talking. Okay.
Yep.
I'm a
couldn't
visual
possibly
learner. That's
write that
why I
fast.
was asking. I was like, wow. But I was just like, I'm a visual learner. I like to see things when it's happening. That's why I was asking.
Okay, but
You were going
but we
over a lot
agreed
of stuff.
I know.
No, it's
but we
okay.
agreed
We did agree. I understand.
okay.
12
So
and 13, we're going to review.
So I'm just quickly reviewing this stuff, and I'm just looking at the text. So if you want to see something, open the text and look at it. I'm just going through it. Okay, there's more examples, and that's it for chapter 12. Okay, so anything needs to be clarified on chapter 12. So this is just basically the definition of ring and sort of simple properties of rings, together with examples. Okay. Okay, integral domains, so that's chapter 13, is the next. I mean, I can share my screen and we can look at me flip through the book. Just make this a little bigger. I'm not writing anything at the moment.
I just moved my book over to my television screen so I could watch it from there. That's fine. You don't have to show your book. I'm the only one asking about it.
The main thing about integral domains is that they have, so what is a zero divisor? I guess that's the one thing I want to make sure we all understand. So what, if I say A in a ring is a zero divisor, what does that mean?
They multiply to give you 0, but they're not 0
Yeah.
themselves.
So if a
B.
particular element A is a zero divisor, then that means there is some other element B, so that neither A or B is 0, right? And their product is 0. Okay, so let's take a really simple ring like Z6, right? What are some zero divisors in Z6?
3 and 2.
3 and 2, right? Because 3 times 2 is 6, and that's 0 in Z6, right? So there's an example where you have zero divisors, right? Okay, so the kind of thing you can't do with zero divisors, and so let me also write things occasionally. Let's see. So we want to use this other. Okay, out of the way.
Wait, Dr. K, and this
Yep.
might be jumping the gun, but so were they saying that Zn, when n is prime, doesn't have 0 divisors?
That is true, yeah. So
Okay.
that's a thing we want to make sure we understand when it's true.
Okay.
Let me see. I want to open this other. Let's do this one. So here's a really important example, and this will come up if I do this example from the DQs, and I want to try to not forget to do that. When we factor something like this, right, in a ring, so say in Z6 together with X, right? And we want to solve this, right? You can't just say, well, this is equal to 0 means that X minus 3 equals 0, or X minus 6 equals, or X minus 2 equals 0, sorry.
Although that's certainly true, correct?
It is certain, well, this is not true, right? That's not true. It would be true that if one of these things happened, I mean, so this is true. So if X minus 3 equals 0, or X minus 6, I keep saying 6, X minus 2 equals 0, then X minus 3 times X minus 2 is equal to 0, right? But the other direction, right? So if, I mean, it may or may not be true here. I didn't think about it. Let's think about it. You know, so here it's more of a question. So if that happens, so, you know, is it true? X minus 3 equals 0, or X minus 2 equals 0. All right, so the question is, like, is that true? So in other words, like X equals 2 or X equals 3, right? So is that actually true here?
Is it true to say that, like, to go backwards, that if, so you're saying if X equals, or X minus 3 equals 0, or X minus 2 equals 0, then X minus 3 times X minus 2 is 0, but we can't go the other way around.
Yeah. So it's always true that if A equals 0 or B equals 0, then AB equals 0. Why is that true? That's true because one of the things we didn't prove a minute ago, but I said you should go through the proof of, is that in a ring, 0 times A equals 0, right, for any A. Right? So if one of these things is 0, then the product has to be 0, right? And the reason is this, because 0 times A is equal to 0. That follows from the ring axioms, right? What isn't true in general is that AB equals 0 implies A equals 0 or B equals 0, right? So when this is true, then you have, and it's true for all the elements A and B, then you're in an integral domain, right? It means there's no zero divisors, right? But if it turns out that A equals 0 where neither of these are 0, that can happen, right? That means that A or B is a zero divisor, right? So if you have zero divisors, then you can't go in that direction, right? So that's the point. And now up here, is there a way to get, so if I do like 4 minus 2, that's going to be 2. And I do, or let's say 4 minus, is there a solution in Z6? I didn't really, this I just made up out the, like, is there a way to get, what is like -3? So 5 minus 2 and well, like let's see. Yeah, 0. Okay, so 0 is a right. Someone said it, I think, right? So 0 is a solution there, right? So if I plug in 0 there, I get -3 times -2. That's going to be -6. That's going to give me 0, right? So I get solutions 3, 2, and 0, right? And maybe there's another one, right? I mean, I'm not sure. I haven't checked them all, but there might be other solutions, right?
5.
So I do 5, then I get 2 times 3. I get 2 times, 5, right? So, okay, solutions are going to be, so, dang it, x minus 3 times x minus 2 equals 0 has solutions. X equals 0, x equals 5, x equals 3, x equals 2. What about 1? But 1 in there, I get, what, minus 2 times -1. So it doesn't look like that. So the only thing not a solution in Z6 is 1, right? So you see, you have to be careful when you're working in integral domains, right? That's a thing you can't use, right? You have to be careful about this. Okay. Does that make sense? So keep these examples in mind. Keep examples in mind, things like, I don't know, Z8, Z12, Z6, things like that. Right? Did you have a question, Caitlin?
Yeah, so just to clarify, with those 2 bullet points that you wrote there with A equals 0 or B equals 0 implies AB equals 0. Yes.
Mm-hmm.
So you said the second one is only true in integral domains when there are no zero divisors?
Yeah, because this, what does this thing say right here? It says, that A and B are not zero divisors. Right? Because what does it mean to be a zero divisor? It means that you have some non-zero things so that A times B equals 0, right? So if I take this, now we're going to do a little bit of logic, right? This has the form, A implies B, right? So the contrapositive of that is not B implies not A, right? And those two things are equivalent to each other, right? So not this would say A does not equal 0 and B does not equal 0 implies let's see what I want to do. It's not quite the negation, I guess. Yeah. Okay. Sorry. Let's be a little bit more careful about this. Let me do this. What do I want to say here? Well, anyway. Okay, forget the little logic lesson, right? Let's just forget that little logic lesson. But it is true, right, that if for every A and B, if A and B were zero divisors, right? If A is a zero divisor, right, then there is some B. Maybe that's the problem. I've got two things here, and being a zero divisor just requires a single thing, right? So if A or B is a zero divisor, then there is an element, right? So if A is a zero divisor, there is a B such that AB equals 0, and A and B are not 0, right?
Could
So
it
that
be
would. Sorry,
Sorry,
so
could it
that
be-
would be a zero divisor, right? So go ahead.
Could it be possible that there is a different element in the field that is a zero divisor, but it's not A or B?
Yeah, I mean, so this equation, I mean, you could satisfy this thing if the things are, if you know you have, yeah, so if you know you have two things which are not zero divisors, right? So if you know A and B are not zero divisors, right? And AB equals 0, right? Then A equals 0 or B equals 0. Because that's again, that's just the definition of being a not zero divisor, right? So if A is not a zero, I mean, the way you know, I could say like this: A is not a zero divisor implies AB equals 0 implies A equals 0 or B equals 0, right? So if A is itself not a zero divisor, then the only way I can make a product of A that gives me 0 is if one or the other is 0, right? And another thing that says is that if A is not a zero divisor, and AB equals 0, right, then B is not a zero divisor. Right? Does that make sense? Caitlin?
Yes, thank you.
Okay, so anyway, so it is an important notion. It's a good thing to keep in mind as we go on and do stuff, right? Which things are zero divisors? I mean, which sort of rings don't have zero divisors and which sort of rings do have zero divisors? And we'll be spending some amount of time sort of figuring that stuff out, right? So that's a theme that we'll have. Let's see, I lost the book. Here it is. Normal subgroup test. I got way off there. Where am I? Sure how that happened. Oh, we're in 13. Okay, so having zero divisors allows you to do cancellation, right? So that's sort of equivalent, right? Think about that. Why is that true, right? Is that sort of clear? I mean, just real quickly, if I have AC equals AD and A is not a zero divisor, right? Then can I get that C equals D? Right, so that's the question. How do I get that? So here you just do some math, right? You say AC equals AD is equivalent to AC minus AD equals 0, right? And then you use distribution, right? So this is AC minus D equals 0, right? But A is not a zero divisor, right? So if this product is 0, this will mean that C minus D is 0. So it's I mean, you know, as long as A is not a zero divisor, you're basically doing your normal math there, right? So that's sort of the thing to keep in mind, all right? And again, it shouldn't be too unfamiliar because matrices had this same kind of problem, right? So this is something that should be sort of familiar from using matrices. Okay, what is a field? A field is a commutative ring with unity. That where every element is a unit. So every element has an inverse, right? And again, if you have an inverse, the inverse is unique, right? So once you have an inverse, right? So what do I mean? Once something acts like an inverse, right? If A times, first you need a unit, right? You need the unit. But if A times B equals 1, right? Then B is A inverse. I mean, this actually isn't quite true. If A times B equals 1 and B times A equals 1, then B is equal to A inverse, right? With matrices, you got to do a little bit more, even though they're not commutative, right? You got to say if A times B equals 1, the identity in a matrix, then you actually know A and B are already inverses, right? But for arbitrary rings, actually, you need both. You need it to be a two-sided inverse. So you have to be a little bit careful. So when you're doing linear algebra and you use that fact, you actually should prove that if A times B is equal to the identity, then also B times A is equal to the identity, right? And that's without commutativity. So you can't just use commutativity. You've got to do something else to prove that, right? But that's kind of special for vector spaces or for matrices.
Dr. K.
Yep.
How does having no zero divisors imply that every element has a unit?
It doesn't.
So for the every finite.
Sorry. So let's be more specific. So if you're in a finite ring, right, then every element is a unit or a zero divisor, right? That was one of the homework problems someone did. So I mean, we can look at that. And I can even indicate where this kind of false thing comes up. So the proof someone gave is a good proof. So whoever did this problem did the following thing. So let let R be a finite ring. With unity. And you don't need commutativity here. I think in the problem, commutativity was there too. Whoever did this problem can speak to that. I don't quite remember. So what we can do is we can take S to be an element of R.
Okay, I didn't know it had unity. I think that kind of changed.
You need unity for the argument to work. You need unity.
Okay. Well, that makes sense.
So let me just keep going through it here real quick.
Yeah.
So we want to show. So we want either S is a unit, so in the units, or S is a zero divisor. And the proof is actually related to, you had a proof that if you have a finite group and the group is closed under multiplication, then it's actually closed under inverses as well, right? So when you have a finite group and you're checking for like the subgroup thing, right? You can just check that it's closed under multiplication. And for free, it's closed under inverses, right? And the trick is basically, as you keep taking powers, you have to eventually repeat something, right? And then once you repeat something, you show in the group case that you got 1, right? So we're basically going to do the same thing here. So okay, case 1. So this is kind of by cases. S is a zero divisor. In which case we're done, right? We're trying to show that S is a zero divisor or it's a unit, right? So case 2, S is not a zero divisor. Okay. Well, if S is not a zero divisor, then no power of S is a zero divisor. Okay, so let's see that. Okay, so then S to the R is also not, or maybe I just want to, let's see, I don't, yeah, that's fine. Okay, let me prove something else then. I'm going to say S to the R is also, well, no, okay, I'm going to write the same thing, not a zero divisor. Right, so like, why is that true? Well, if S to the R was a zero divisor, then S to the R A would equal 0 for some non-zero A. I guess maybe I have to be a little bit careful. Let's see if I end up having to be a little bit careful here. And so in that case, S times SR minus 1 A would also equal 0. All right. But then what is that telling me? But S is not a zero divisor, right? So that would be telling me that SR minus 1A equals 0, right? Because S is not a 0 divisor, so I can cancel that S, right? So I get SR minus 1A equals 0. So maybe I need to be a little bit careful and say, let R be sort of the least thing, right? So that S to the R equals 0. So sort of backtracking. Actually, do I need to do that? I mean, it's kind of an induction thing that I'm doing here. Yeah, okay, let me pretend I was doing induction, right? So I could sort of minimize the least counterexample, or I can do an induction, right? So suppose I knew that S to the R minus 1 is not a 0 divisor, right? And you can sort of view this as a proof that S to the R is not a 0 divisor, right? So if S to the R minus 1 was not a 0 divisor, and we know that A is not 0, then this thing can't be 0, so that would be a contradiction, right? And so since that's a contradiction, we get that S to the R, A also can't be 0, right? So by induction, right, S to the R is not a 0 divisor for any R. Okay, did that make sense? I mean, I had to do something right in the middle that kind of I got stuck on, right? I'm taking S, which is not a 0 divisor, right? And I'm showing by induction that S to the R is not a 0 divisor, right? So the base case is 1, and that's given because that's what I'm assuming, right? S to the 1 is not a 0 divisor, right? And so now I'm assuming S to the R minus 1 is not a 0 divisor, right? And then I showed that S to the R, which is S times S to the R minus 1, is not a 0 divisor, right? The other thing you could do is do a minimum counterexample, right? Suppose S to the R was a 0 divisor for some R, right? Then factor it into S times S to the R minus 1. Well, one of those has to be a 0 divisor, right? And that's a contradiction to the fact that R was supposed to be minimal, right? So that's a different way of doing it, right? Everyone shake. I mean, induction shouldn't be a new thing, right? Okay. Okay, so S to the R is not a 0 divisor. Now we can use that trick that we used in the groups, right, to prove that a finite group which is closed under product, finite subset of a group which is closed under product is actually already a subgroup, right? And so we'll do the same trick we had there. So I take S and I start building S2, S3, etc., right, up to Sm, right? And at some point I've got to repeat something, right? Because the set's finite, right? I can't keep going forever and getting new things, right? So at some point I have to repeat. So let M be the least thing that repeats, right? So what I get is that I get SR equals SM, right, for some R less than M. Sorry, that's an R, that's an M. Does that make sense, right? I start with S, I look at S squared, eventually I've got to repeat, right? Again, this is not a new argument, right? This is one we did with groups, or I mean, you did with groups, assuming you read the book and stuff, right? Does that make sense? Everyone nod or thumbs up or something, right? Okay. Well, if this happens, right, then I can do what? I can subtract. Let's do it like this. Sm, remember, M is bigger than R here, minus SR is equal to 0, right? So now I've got my 0 there, right? And then I can factor out an SR, right? Because these are just products of S, right? So this is SR times Sm minus 1 is equal to 0, right? So I'm just using the algebra, right? But what did we just show? We just showed that this is not a 0 divisor.
Should we have S to the M minus R?
S to the M minus R, yes. Sorry, that is important. Is a 0. So this thing has to be 0, right? Sorry, S to the M minus R minus 1. right? Okay, so we're almost done. So S to the M minus R is equal to 1. Okay, so I guess the only question here is M minus R bigger than 1? Right, so maybe that's a question, right? So if M minus R is bigger than 1, then I can factor out an S, right? I get S times S to the M minus R minus 1 time equals 1, right? And in that case, this is S inverse, right? And again, now we're using the fact that our S inverse was unique, right? And and actually, to show that this is S inverse, I really need to do this on both sides, right? But I could do the same calculation and get S to the M minus R minus 1 times S is equal to 1, right? Very same calculation, right? I'm just sort of changing the side at which I'm doing something on. Okay. So we have an inverse in that case. The only little point now is that I needed M minus R to be bigger than 1. Let's see if I get in trouble there, right? So if M minus R equals 1, then what do I get? I get that M equals R plus 1. Okay, so that my original thing up here was just SR plus 1 minus SR equals 0, right? That's what I'm getting there, okay? But then I'm getting that SR times S minus 1 equals 0, right? And that would be telling me that S equals 1. In that case, S equals 1, but 1 definitely is an inverse, namely itself, right? So S inverse is also just equal to 1. Okay, so there was that one little, these kind of like little things that come up like that, like, okay, everything works except I need this extra little box there, right? So this thing is what we often call an edge case, right? It's a little thing you have to deal with that just causes a little bit of trouble, right? But it's has to be dealt with, right? So just sort of reviewing this, right? The assumption was if S is not a zero divisor, and then some work, right? Then in either case, we get an inverse. Either the inverse is this, just some power of S. So not only do we get an inverse, but the inverse is just a power of S, right? I mean, we could even make that stronger claim, right? The inverse is just some big enough power of S, right? Or S was just 1 to begin with, right? In which case it has an inverse. Okay, so you might want to think through that again, but that's how it goes, right? So that's how it goes. Okay, so in a finite ring, and commutativity was never used here, right? But having a 1 definitely is used, right? So in a finite ring, every element is either a unit or a zero divisor. But now that's special for a finite ring, right? Okay.
Dr. K, the proof I used for that one, I got help with it, but I understood it a little more than that one was a mapping with
So,
A being the.
I know exactly that. And if you look at the DQs, I made a comment about this. So let me do something and tell me if this isn't exactly what you did, right? So we define phi going from R to R. And this, by the way, is the one you find when you search, and it's the one that everyone finds that isn't quite correct. And I'll show you why it's not correct. Now, there may be a way to correct it. I haven't really thought much about that. But the argument is this: I'm going to define phi of S for S and R to equal R times S, right? So maybe I could even call this phi R of S, right? Because R is fixed, and then I'm mapping the rest of things by just multiplication, right? So if we were doing groups, this is like a left action by multiplication, right? Okay, then phi going from R to R. So now you do have to prove some things. You have to show is a homomorphism. So you need to use some facts about homomorphisms for this argument to work, right? That's easy to show, right? Because what you need to show that phi of S1 plus S2, is phi of S1 plus phi of S2. Actually, let's see. We're just going to show that it's a If I'm just going to show that it's a group homomorphism, right? I think I'm in trouble if I try to show if it's a full homomorphism, right? So it's a homomorphism of the additive group, right? Is all I'm actually going to show here, right? Okay, so this is but what is this? This is R of S1 plus S2 equals RS1 plus RS2, right? So that definitely works, right? So that works. And then, you know, phi of 0 is 0, right? You can check that. And phi of, I'll just leave these for you to check. Minus S is minus phi of S. It's easy to check those things, right? Okay. So phi is 1-to-1 if and only if the kernel of phi. Now we're just looking at the group part, right? The kernel of this phi is the identity element, which in this case is just 0, right? Okay. But what does it mean to say the kernel of phi is the identity element? It means that the set of all S such that RS equals 0 is just 0, right? So this says the only way to multiply by R to get 0 is to multiply by 0, right? That's exactly what it says, right? So this says if and only if R is not a 0 divisor. Right? So this map is 1-to-1 if and only if it's not a 0, if and only if R itself is not a 0 divisor, right? But since it's finite, if it's 1-to-1, it's got to be onto, right? So now we have that, you know, R is not a 0 divisor if and only if phi is 1-to-1, if and only if phi is onto, right? But if phi is onto, then that means that phi of R equals 1. Sorry, phi of S equals 1. And I've got to say, I was calling this phi of R, right? For some S. Right, and that implies that RS equals 1. Right? So if we were assuming commutativity, then we're done, right? We have an inverse. All right, if we're not assuming commutativity, then you need to do something else to also argue that SR equals 1 for the same S, right? So that's the thing where we have to be a little bit careful here. And you might be able to do that. I just haven't thought about that too carefully. Okay. But this is kind of the standard proof you get. Is that right, Jordan?
Yeah, I was just saying I could follow that one. Like I understood it, you know.
But you
I
should be able to
probably-
follow the other one. All the other one did was take powers of S.
Oh, you're
right?
breaking up.
And show that one of those powers had to be an. So it is thinking about this. Useful why any finite integral domain is a field, right? That'll be a corollary of this, right? Because in an integral domain, everything is not a 0 divisor. So everything is a unit and therefore it's a field, right? So that's important. But then that very same argument was also used to show that every finite subgroup, every finite subset of a group, which is closed under whatever it is, addition or multiplication, right? Has an inverse. So it's the same argument. It's sort of just taking powers. It's looking at the cyclic, I mean, the multiplicative part isn't a group. So we're not looking at the cyclic subgroup, but we're looking at something like that, right? So I mean, up here in this argument, I'm basically looking at this S where if we're thinking about group-like things, right? And this would be like powers, you know, for I and Z, right? But this is a finite set, right? So this is finite, right? And we just have to argue that one of those has to do what it needs to do, right? So it's it's a useful argument too. They're both very good arguments, right? So it's good to kind of understand both. Okay. So back to the book. Okay, any questions about that? Okay, a field, we've already said it's a commutative ring with unity in which every element's a unit, right? You might also want to think of it as an integral domain in which every element's a unit, right? Because integral domains are commutative rings with unity, right? So when we say integral domain, that's what it means, right? Commutative ring with unity, right? With a 1, right? So to be a field, you need to be a commutative ring with unity where everything has an inverse. Good?
I think in the books, it also said that finite integral domains are the same thing as fields.
Well, that's what we just proved, right? Because we just proved that any finite ring with no, and we proved something a little bit better. We proved that any finite ring, well, sorry, we have to be a little bit careful. So we proved that any finite ring with no zero divisors has every non-zero element has an inverse, right? We proved that, okay? We're not assuming commutativity there. We do need a 1, right? We needed a 1 in that argument, but we're not assuming commutativity, right? So we're not getting a field, but we're also not starting with an integral domain. When you're looking at a thing where every element is not a zero divisor, I'm not sure what name that has. When you're not assuming it's also commutative, I don't know if that has a name. But when you have a non-commutative thing, where everything, so you have interesting non-commutative rings where every element has an inverse, right? So those are also not fields because they're not commutative, right? And they're really useful things. So if you know this sort of stuff, you've got you take the reals and you build up to the complex numbers, right? And then you build up to something called the quaternions, which we did look a bit at in the group theory because we looked at the quaternion group, right? But the quaternion ring is used, for example, when you're doing graphic programming, right? Because it's very useful in coding sort of the way rotations and stuff in 3 dimensions, right? That's a ring where every element has an inverse, right? But it's not a field because it's not commutative. It's a non-commutative ring, and those are called division rings. Okay, so that gets a name, right? So sort of in words, what we showed that every finite ring either has zero divisors or is a division ring. That's what we showed, right? And then if you don't have zero divisors, that means you're an integral domain. So we showed that every finite integral domain is a field, right? So the only difference between a division ring and a field is commutativity.
And then, Dr. K, I think this chapter ended, we probably about to get there with characteristics. And that, how do you get the characteristic of a like a ring polynomial? Because a question.
Okay, that's a good question. That's a good question. Let's see. So let me not skip the next thing, and then let's talk about that. So the next thing in the book, I just don't want to skip it, is that Z, because this is important to know, is that ZP is always a field for a prime P, right? And you know that because that is Bezo's theorem, right? Bezo's theorem tells you every non-zero element has a multiplicative inverse relative to a prime, right? This is something we've done since day 1 in the class, okay? So that field definitely has multiplicative inverses. Okay, yeah, the characteristic, so there's kind of 2 definitions. One definition is the least in, right? So let me write something here. So when you're looking at the characteristic, you're taking an arbitrary x, and you're looking at x plus x over and over and over, right? And if there is an n so that you get to 0, right, then what we would write here is we would write nx, because there's n copies of x, right? So notice that this is not multiplication in the ring. This is in R. This is in Z, right? So this isn't ring multiplication. This is just n copies of x, right? And the character of R equals the least n, if there is one, such that nx equals 0 for all x. Okay. I think rings can have kind of funny characteristics if the ring doesn't have a unit. Okay, so let me just kind of sweep that under the rug and say, we're only going to really use this for the most part for rings with units, right? So when we're in a case with a ring with units, right, then this x plus x plus x plus x can be turned into n times, well, sorry, it can be turned into x times 1 plus, or let me turn it around. It's 1 plus 1 plus dot 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 plus 1 x, like that, right? So it can be turned into that thing. And we're asking when that is equal to 0, right? And we're looking for the least thing where that is equal to 0. And so that's going to correspond to the least thing where n times 1 is equal to 0. Right? So we're looking at that sort of situation. And so when we have a unit, a 1, right, then we get that the characteristic of R is equal to the least n, such that, you know, n times 1 is equal to 0. Right, so we get that. Right, because if I take any other x now, right, if I take any x at all, and I look at nx, I can rewrite it as, you know, 1 plus 1 plus 1 plus 1, many x's, and that's x plus x plus x plus x, right? But this is equal to 0 times x, which is 0, right? So definitely n times x is equal to 0 too, right? On the other hand, if I take any x plus x plus x plus x, which is equal to 0, right, I can write this as 1 plus 1 plus 1 plus 1 a bunch of times x equal to 0, right? And so whatever this is m times x equals 0, right? But that means that this m is bigger than that characteristic, right? So this n, right, whatever the least, if I have a unit, then I don't have to look at all possible x's, I just have to look at 1. Can I add 1 to itself a bunch of times and get 0, right? So that's that.
So would that n be a 0 divisor?
This n, it depends on whether or not, I mean, it could be that n, so this n here, yeah, n gets used in two kind of related ways. Okay, I mean, sorry, there's lots of little things that come out here. So jumping ahead a little bit, we're really kind of defining a map from Z into our ring, right? And the map is going from n to n times 1, right? Which we're viewing here as 1 plus dot 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 plus 1, right? So we're sort of viewing it like that, right? So it's just n many copies of 1, right? So maybe I leave off this little dot. I mean, here we almost need like 2 different symbols, right? So just n copies of 1, okay? But this isn't the one of, so this is in Z, right? This is in R. So if I want, I could put little R's down here. This is the unit of R, right? And so when I add these units of R, I get this sort of n sub R, like that, right? So I get a map, phi, going from Z into any ring with unity, where n is mapped to this kind of nr kind of thing, right? Now this nr, this copies of 1s, that would be 0 in the ring, right? This would be the 0 of the ring. Because that's, you know, if this happened, right? For the characteristic, that would be the 0 of the ring, right? And so what we're getting here is we're getting, in this case, that we're getting a copy inside of R, you know, like the range, the image of phi here would be Zn, right? So in other words, R would have its little version of 0, which is just 0, the 0 of the ring, 1, which is the 1 of the ring, right? But it would also kind of have a 2R up through n, well, n minus 1R, right? So you should start seeing like modular arithmetic here, right? All the way up through those things, right? These would
Dr.
be.
K, did you do this exact example in your video where you said be careful because whereas 3 plus 3 is 6? Is this the exact same example that you did in your video?
Well, I'm not looking at a specific case here, but I did in the video talk about embedding Z into the ring, right? So that's all I'm doing here, right? Is I'm saying
I'm
The
just
ring
trying to
has a
connect the
1.
learning.
the ring has a 1, so we can add 1 together a bunch of times and get sort of in many 1s, right? But that gives us a copy of M inside of R, right?
Okay, so those are like actually the number R. Those are like the units in the ring of
These
R.
are well, they aren't the units. These aren't units at all necessarily, right? But these are elements of the ring, which are basically behaving like Zn, right? I mean, it's behaving like a little copy of Zn inside there, right? So what it's saying is every ring with a unit either has a copy of Zn, where n is the characteristic, right? So Z, characteristic of R, right? Sort of sits inside of the ring like this, right? The other option is that, what do we say when there isn't such an n? We say the characteristic of R is 0, right? When there is no such n, we say the characteristic of R is 0. In that case, we have Z, a copy of Z sitting inside of R, right? Because for every one of these things, I just map into the sort of R version of n, right? And the corresponding, I mean, this was for positive n, but then the minus n would just get mapped to the minus R version of n, right? So we have a little copy of Z sitting inside of the ring, right? So either Z sits inside of the ring as a copy, defined like this, right? Or Zn sits inside of the ring as a copy. That makes sense? We're just using the fact that we have 1 and we can add 1s together, right? That's really all we're doing, right? Okay. Now, when you're asking which one of these things are 0 divisors, right? That depends on what the characteristic is, right? So if we're going into the ring and the characteristic, char R is 6, right? Then what we're getting here is just 0R through 5R, right? Then we're getting a situation like that, right? And then some of these things are 0 divisors, like 2R times 3R, right, would be 6R, which would be 0, right? So that would be a 0 divisor in that case. Does that make sense, Hugo? Right, so depending on, so that's why if the ring is an integral domain, then the characteristic has to be prime for exactly that reason, right? So if R is an integral domain, then our copy that's sitting inside there, right, our Z in let's say n equals char R, our little copy Zn, which is sitting inside of our ring, right, is now has no 0 divisors.
So I gotta be prime.
And so it's a field, and so it's got to be some ZP for P of prime. Those are the only ones that don't have 0 divisors, right? Because if I have a Z, if I can factor my n, right, then I can clearly find a 0 divisor in there, right? If I can write n as m times R, right, then m and R are going to be 0 divisors, right? So the only way we can have this work out if R is an integral domain is if this n is prime, right? Or if the characteristic is 0, right? The characteristic could be 0, right? Okay, so like Q has characteristic 0, right? And Z is embedded in Q, right? Okay. Okay, I didn't quite answer. Someone asked the question, and I haven't thought about this. I'm thinking maybe it's not good to try to answer it on the fly.
Yeah, it was a question in the next section that asked for the character of a quotient group. I mean a quotient ring, but the ring was a polynomial. So I was trying to figure out how to find or it asked if the quotient of that divided a squared plus b squared. That's what the question was. And I think you're on mute.
Sorry about that. I did
You-
accidentally push the button. Okay, I know what problem you're talking about. And let's see, that's not such an easy problem. So if you look at the notes that I suggest you look at, I have this whole set of notes on the Gaussian integers, right? And that came up from that problem. Okay. So it's not a completely trivial thing to answer. So let's get there. And then maybe I have to look at the answer that I actually have written out, and then maybe we can figure out what the easiest answer is there. But that one actually takes a little bit of effort. It's not a freebie, that one. Okay, any questions about what a characteristic is, right? We're just adding ones together till we get 0. If we don't ever get 0, we might want to call it an infinite characteristic, but we call it characteristic 0 instead. Okay. Whatever the character is, we have a copy, if the character is characteristics in, then we have a copy of Zn sitting inside of our ring, behaving just like Zn does, right? So that's a useful thing to have. And if the ring is an integral domain, then that copy of Zn has to be an integral domain, and therefore has to be Zp. It has to also be a field, right? Because it'd be a finite integral domain. The ring itself doesn't have to be a field. The ring doesn't have to be finite. Infinite rings can have finite character. Okay, so don't make that mistake. You might have an infinite ring with finite character. It contains a copy of Zp for some prime p, right? Okay. Everybody got that? Be good on that? Okay. So we're not exactly.
Can you say it
flying.
one more time? Say that one more time.
So I said a lot. So let me. so for every
Infinite rings.
So there are infinite rings. With finite character. Don't ask me to come up with one on the tip of my tongue. Sorry, there are infinite rings with finite character, right? So there are rings R, which are infinite rings, right? But which have a copy of Zn. So that, I mean, if Zn's sitting inside there, N has to be the character, right? N equals P for some prime. I mean, I'm assuming here that this ring has a unit, right? Otherwise, things get a little weird, right? So this is an excellent question to ask offline for me to come up with an example. And I would probably go ask the AI, give me an example of such a thing. Because these are the sort of things it's really good at. That I don't keep them on the tip of my tongue, right? But there are infinite rings with finite character. And they're probably not too hard to come by. I just haven't thought about it. Okay. Good. Let's go back to the text a little bit. Okay, so I think that's it. Yep, characterism in integral domain. Okay, and then that's it, right? So now we did make it to 14, which is good. Unfortunately, we've already used an hour. Now, actually, I do think that all of this is also kind of should be mostly familiar. Like nothing we're doing today looks that much different than what we did with groups. So I'll try to sort of couch it that way.
Don't go too fast, because this was the part of groups where I struggled when we got to factor groups is where and homomorphisms is where I started.
Okay, I mean, it's a thing to see over and over because, I mean, again, these are one of those things that's going to repeat over and over and over as you do math, right? So you're doing this when you do real analysis, you'll have homomorphisms and, all that sort. So you're always looking at structure preserving maps, right? When you did linear algebra, you had linear maps. A lot of linear algebra is just about linear maps, right? And lots of people would say what you study in math is the maps between structures inside of a structure. So sort of studying which homomorphisms there are, which isomorphisms there are, is kind of what you do a lot of the time when you're doing math, okay? So it is worth learning over and over and over because what you want to get used to seeing is the similarity that keeps coming up over and over and over each time you do it. so that it becomes, so that it should start becoming like, oh, I've seen this before in this other context, and it's obvious to me at this point, right? So, I mean, don't forget linear maps from linear algebra. It's the same notion, right? You're looking at structure preserving maps for homomorphisms, right? And if it were me, I would introduce homomorphisms first and then introduce factors, because that's sort of the natural way of doing it. But the book flips things around. So let's just go ahead and do it that way. Okay. So we're in the situation, we're in a ring, right? So we have a structure, we have a 0, a plus, and a times, right? And we want to construct some kind of quotient ring, right? Well, among other things, we need the quotient to be a quotient on the group, right? So when we look at this, quotient, I'm using I because we're going to use the word ideal, and so that's common. That I need a 0 and plus, and we need this to be, sort of the quotient group. We're just looking at the group part, right? So now when I say this should be familiar, it's because you just did this in group theory, so this should be familiar, right? Now we got an additive group, right? So the cosets, right, are of the form R plus I, right? Because we're in an additive group, right? So the cosets are the form R plus I, right? And the way this works is we're going to have R plus I, Okay, so first of all, I mean, there's all this sort of stuff we've already done. It defines an equivalence relation, right? So we're taking our ring and we're breaking it into equivalence classes, right? And over here is an equivalence class with I. That's like the, normal subgroup, right? Because I is also a normal subgroup, right? Because I's got to be a subgroup in order for this to work. Because here I'm just looking at the group part. I haven't talked about the multiplication part, right? I'm just looking at the group part, right? So I has to be a normal subgroup, but this isn't a Abelian group, so every subgroup is a normal subgroup. So that's good, right? To be a normal subgroup, there's the bit with I. Here's the A plus I, for some A. Here's a B plus I, right? These are the cosets, right? And left coset, right coset, it doesn't matter because again, we're in a commutative setting for the plus part, right? Okay, and then we can turn that part into a group just like we did before. So if I want to take R plus I and I want to add it, so this is like in our new factor thing, right? To some S plus I, right? So the objects are actually these classes, right? Those are the new objects. These classes of things, right, are the new objects, right? And then we're defining this new thing. I'm defining this new plus, and well, all this is going to be is R plus S, plus I, right? And again, this is just coming from the group part, right? Okay, so all of that is just from the group part. And if I want to know, I want to know if R plus I is equal to S plus I. Well, how does it work in the group? We just say, is it true that R minus S is an element of I, right? That's how it worked with the groups, right? For additive groups. Okay, now the trick here is when we were doing the group theory, we tended to use the multiplicative notation a lot, right? So now we're sort of specifically using the additive notation here. Okay, so in order to make a ring, right? So now the question is, what do we need to have happen so that I can do the same sort of thing to make a ring, right? So I need R plus I. I would like to define R plus I, S plus I to equal RS plus I, right? I would like that to work, right? What do I mean work? I mean, yeah, what do I mean work? What does it mean to say I would like that to work?
You would like for the product to be an I? Is that what you're saying?
No. I want this to be, I want to define a product. So we've got all the group stuff, right? So now we're going on to the ring stuff. And all I need to do is define the multiplication. So I need to find the multiplication in the ring. And I want to do it just like we did for the groups. I want to say that the coset that corresponds to the product is just the corresponding coset of the product of these things, right? All right, I've got some operation. I want to extend this operation to the quotient structure, right? And the way I would like to do it is to just say, well, I'm going to take the product of this, and all I'm really going to do is take the product of the R and S and, look at that coset, right? We do this, I mean, this is exactly what we do, right? Zn is really Z mod nz, right? And the things that are in here, right? And I did this like on the first day of class, 1 bar, 0 bar, 1 bar, 2 bar, up through n minus 1 bar, right? Is really just 0 plus nz, 1 plus nz, right, etc. I mean, if you go back and see what we did at the first, right, we did exactly that, right? When are two of these things the same? We have that, n plus m, n plus, sorry, let's try I and k, right? I plus nz is equal to k plus nz, right? So this is just saying that I equals k mod n, right? And and that's going to be if I minus k is in nz, right? So this is if and only if n divides I minus k. So think about this case, because everything we're doing now is like this, right? Okay, so that was the group part of that, right? But we also can do modular products, right? We've been doing that, right? How do we do modular products? If I do I bar times j bar, right? The way we've been doing that is do ij, mod n, right? Same kind of thing. So we're really doing is I plus nz times j plus nz, right? And what this is supposed to be is ij plus nz, right? And this is what we've been doing. So, I mean, we've been using the product structure of Zn all along, right? Because we've been talking about Zn and Un as the corresponding multiplicative group, right? So we've been using this. So don't, keep that intuition of that particular example in mind, right? Okay, it's important to keep good examples in mind when we're doing this stuff. So in general, right, so I've got R, I've got I subset of R. All I know so far is that I is a subgroup, right? That's all I've done so far is the subgroup part, right? But now I want to define, I'll say it again, I want to define R plus I, S plus I to equal R, S plus I. And I want this to be a good definition. What does good mean? And now I'm trying to get you to tell me what good means, like I'm trying to extract it from you. What do I need to have happen here to make this work out so that it makes sense? I mean, I'll give you a hint. Suppose I had two of these things that are the same. Then what had better happen? What had better result? It better be the case that what else is the same.
Is it that R prime S prime plus I is equal to RS plus I?
Yep. If I'm going to define this as my product, then it better not depend on which representation I take, right? Because when I'm looking at cosets, I can represent the coset by any element inside the coset, right? It's any element plus the subgroup, right? So that's all that's going on. But if I'm going to define the product like this, it had better not depend on which choice I take for the representation, right? So this means it's well defined. And so we need to be well defined, right? So now the question is, what do we need to get this? Okay, so that's what we want to look at here. So here I'm going to have, so I can rewrite this as R minus R prime in I, right? Because that's what it means for these two to be the same coset, right? I can rewrite this as S minus S prime in I, right? And what I want is I want to get RS minus R prime S prime is in I, because that's what this side is, right? That's what I want to get, okay? And now we're going to do some little algebra where I'm going to add in 0 and then do some math, right? So this is sort of a common trick you do with algebra. I didn't even think about this ahead of time. So if I make a mistake, but I think I can do this in almost any way. So I'm going to just add in r prime s. Subtract out r prime s, add back in r prime s. So that's 0, right? So I've added in 0. And I'm going to subtract r prime s prime over there, right? And I'm going to rewrite this as r minus r prime, r minus r prime s plus r prime s minus s prime. And so this is the same as rs minus r prime s prime.
Dr. K, if you're doing the same math, if you're doing distributive property with that, wouldn't that negative and negative for the prime, R prime and S prime become positive R S prime? Positive R prime, positive S prime.
But here I'm taking out an s.
Right
And here
here
I'm
where
taking
you
out
get
an
the
R
very end, at the very end where you got R prime S. I'm trying to figure out the algebra you did. I'm just being honest. I don't know where you're getting the math from. I don't see it.
Okay, how do I factor in s out of that?
It would just leave me S equals R minus R prime.
I'm not solving
S.
anything, I'm factoring. I'm just factoring.
Right, I would factor S out, open parentheses, R minus R prime.
So we don't have commutativity, so we can't do that. We have to keep things in the same order.
So
So
I
it's
guess
gonna
that's
be-
why I'm lost.
Well, we don't have commutativity, so you can't use that, right? But we can
Oh,
factor
so
in
the
that
S has to
direction.
be at the bottom.
Well, it has to
I
be at
just
the
had
right.
an aha moment. Okay, now I get it. That's why
This
it's
r prime has to
always-
come out this side, right? Because this is r prime s minus
Oh.
r prime. So the r prime has to be on that side.
We tell them bad in high school. We just tell them to put that S in the front.
Well, because you're working in high school in a commutative setting, so you don't have to worry about it, right? But here you do, right? That's part of the point. You have to worry about it here.
But if we taught them right in high school, they wouldn't be confused like me right now when they get to this point. That's all I'm saying. It's a quick
Yeah, I
fix.
mean, I don't know where.
That's what your
I've-
one of your voice audio podcasts said, that if we just really understood the foundation on how this was connected to what we're teaching in high school, we would do a better job of laying a foundation in high school that would help them when they got to grad school. And now I see why the podcast said that.
Yeah, I mean when you actually teach this stuff in school, I feel like it's more like 6th grade when you're teaching
No, this is
basic
algebra 2.
arithmetic. Yeah, but when
No,
you
this is
really
algebra
teach
2.
distributivity and stuff like that.
Algebra 1 and algebra
numbers.
2. Algebra 1 and algebra 2, they don't call it distributive property in elementary. They call, when we start using letters and variables, and as a matter of fact, all they use in high school most times is X and Y. They don't use the literal, like we would call this literal problems where you use anything other than X and Y. And they do that in physics, but in algebra 2 and a little bit in pre-cal, we start changing up the variables from X, but this is not I
So-
understand what you're saying, but it's not an elementary concept for elementary and secondary education. Not in Texas anyway.
Right. So using variables that aren't just X and Y is something that should be done throughout high school, because that does cause a lot of trouble later on. Because it's just silly to think the only variable I can use is X and Y. That's just a silly thing. But here you're really thinking about these as numbers, not as variables. And when you're talking about doing distributivity over numbers, I think that's more like 6th or 7th grade. Because we're not we're not solving an equation with an X here. We're doing, I see Megan saying 7th, so,
Well, I don't
but-
teach middle school, but they don't use the word distributive. Megan, what state are you in? Because they don't do that in Texas. That's all
I'm in
saying.
Missouri.
very close to Texas.
Not 8 hours.
Oh, I used to drive from Texas into Missouri often
Yeah.
enough,
Was it like a
'Cause-
12-hour shot?
because the mountains are right over there. You can't do any hiking in Texas. You have to go to Oklahoma or Missouri to do anything.
But you were coming from southeast Texas, so you shot up through Louisiana straight into Missouri. That's what you did. You were
No,
coming
I was
from
coming.
College
I
Station.
was coming from Dallas. So
Okay, well that's where I live. I still don't see it as that close. But anyways, back to the lesson. Back to the lesson.
Yep.
I'm just saying that this made the point that you said in the podcast. It just gave me an aha moment because I kept trying to understand why you keep saying left and right, and this makes sense since the S is on the right hand side. I would have to factor it from the right hand side.
Okay, so let me review since we had a little break there. So we're starting with this side. So I want to prove this implication, right? So I'm taking this. I want to show it's in I. Now we haven't put enough information into I yet to verify this. We're just trying to see what we need to do in order to verify it, right? So messing with it a little bit, I get it into this form. Well, this thing here is in I. This thing here is in I, right? That's our assumptions right there, right?
Mm-hmm.
So what I need is I need that something in I times anything in the ring plus something in the ring times anything in I is in I, right? So what I need here is I need that I times anything in the ring. So remember this notation is just the set of all, A, R, where A is an I and R is an R, right? So it's just the product of all those things, right? Plus, so now I'm adding anything of that form over here, RA, right? Where R is an R and is an I. Right? So they're flipped around there, needs to be contained in I, right? That's what I need in order for this thing to be an element of I, right? And that's what the ideal has to satisfy. So I subset of R is an ideal. And it's a two-sided ideal because we want both of these. And that's all we're going to care about in this class.
But doesn't ideal say we have to have multiplicative inverse?
Nope, not at all.
Not the notes I took yesterday.
So we need I to be a subgroup. So the additive part needs to be a subgroup of R. And 2, we need that IR and RI is contained in I, sorry, not R. Right, so we need that. Now you can look at this in various ways. You could replace these with 1. I is a subring because I is definitely closed under multiplication. It's actually closed under multiplication by anything in R, right? Not just anything in I, but anything in R gets you back into I, right? So I is behaving like 0, right? So like multiplying by anything in R gets you back in I. It's becoming like the 0, right? Okay, and then secondly, you still need this. You still need this thing. IR and RI is contained in I. All right, so that's an optional, I don't know, 1' and 2'. You could check those, right? So if those two things hold, then this multiplication is well defined, and you can keep doing some work and show that you got a, the distributivity holds and all this other stuff, right? And I could do that, but that would definitely use up the rest of the time. So I think the fact that it's well defined, if these two properties hold, is the main thing, right? I mean, for example, if we wanted to show distributivity, right, I need to show like S plus I times R plus I plus T plus I, right? Let's just see what we need to prove, right? Should equal S plus I times R plus I plus S plus I times T plus I, right? That would be distributivity in R mod I, right? Because I'm taking this thing and distributing it over those two things, right? Okay, but now what does this turn into when we sort of unpack it with our definitions? Well, so I'll do it one bit at a time, right? S plus I, and then this stuff in here is going to become R plus T plus I, right? And then, and so that's equal to this. I'll just prove it. So we're going to get to this one at the end, right? So this top line right there, right, is equal to that thing right there, right? And that's equal to S times R plus T plus I. And all I'm doing is using the definition of how we're doing addition and multiplication, right? And this is equal to Well, this is equal to SR plus ST plus I. Now, why is that true? Well, that's distributivity in the ring, right? I'm just using the fact that the ring is distributive, right? And then I unpack the definitions in the other way. So this becomes SR plus I plus ST plus I. So see, I'm just using the definition of how addition and multiplication was defined there, right? And then this thing I unpack into S plus I times R plus I plus S plus T, plus I, sorry, T plus I, which is what I wanted, right? That was this side. So we've got equality between all those things, and so they're the same, right? So that's how you would prove, for example, distributivity, right? And so all the other pieces are the same, right? So you get a ring this way, right? I mean, is at least this proof clear? Because I think
Yes.
these are good exercises for you just to do yourself if you want to do more, right? Just convince yourself that associativity holds and all these other things. It's all done the same way, right? You just sort of use the definitions together with the property inside the ring. Go ahead. Was there a question?
This just looks very similar to like the properties of modular arithmetic.
It's
Like
exactly
that
the
we-
same. Yeah, it's
'cause
exactly
I remember
the same.
seeing this
Yep.
with in our not as probably not 101 course, but the course that you did with us at the beginning of the program.
Yep.
When we were
So-
talking about modular arithmetic, this
yep.
looked very similar to that.
Yep. So I mean, this is a good example. Yeah. So if I take Z, right, and I look at NZ, okay, is this an ideal? Or is NZ an ideal, right? So this is just, what is NZ, right? It's just, 0, n, 2n, etc., right? Minus n, etc., going that way, right? That's NZ, right? And is it a subgroup, right? So is this a subgroup of the additive part? If I take two things in there and add them together, do I stay in there?
Yes.
Yes, right. If I take something in there, is its inverse in there?
Yes.
Yes, right. Is 0 in there?
Yes.
So it's definitely a subgroup, right? Is it the case that if I take anything in Z, so any K in Z, and I do K times NZ, right? Is that still in NZ?
Yes.
Yes, right. Because what would I, something in
Because you
here is
can
of the
log out
form
from it.
n times I, but n times I, right? So I do K times n times I. Well, that's the same as n times K times I. And that's definitely an NZ, right? And I don't need to check the two-sidedness because, well, this is a commutative case, right? So I don't have to worry about checking both sides, right? So NZ is an ideal, right? One of the things we'll show next time is that every ideal is of the form NZ for some n. So that's what will be, that will get us something called Z is a principal ideal domain, right? So that's part of like next week's stuff. That's kind of where we're headed, right? Is because when we go to fields over a variable, we're going to show that these are PIDs, right? And so they behave a lot like Z, right? That's where stuff starts getting interesting. Good. Okay. Any questions about that? Now, Jordan asked for a specific example, which I can get into. Let's see. One thing I haven't said anything about yet is given a ring. Let me just do this real quick. Given a ring with unity, actually, probably your example, Jordan, is maybe too much. I mean,
Yeah.
I remember that problem as being a little bit because what I want to do is I want to look at ZX mod. It's kind of jumping ahead a bit, so it's x squared plus 1, right? So I really need a lot of stuff to sort of talk about this well, and this is going to be basically the same as ZI.
So can
Right,
you
and
make a video and post that in the class, Dr. K?
I did. It's already there. I mean, this is the Gaussian integers, and that stuff is already in the notes.
So I get
Maybe
this
I
one.
missed that.
This one was dealing with complex polynomial, or no, this was complex. It had a complex
So
I
So
idea.
yeah, zi is, that's what I mean here, right? It's a set of
Okay.
all n plus mi, where n and m are in
Okay.
z,
Okay.
right? This is the Gaussian integers, right?
Okay.
That's true. Okay, maybe we don't quite need it in this form yet. This is what we'll be doing soon. But then the question was here, when you
Does it?
look at an ideal, yeah, I mean it's a tricky thing to answer. Let me do something else first.
Okay.
Actually, I probably should say something about homomorphisms before I run out of time. And then I kind of wanted to look at the solving quadratic because that's kind of simpler, right? And then this one, either come back to, again, I do have some video already on the Gaussian integers, or start there next time, right? As an example, okay? Because it is a really good example, but it can become complicated. Okay, let me quickly say something about homomorphisms, and then look quickly at the just solving a quadratic in various ZNs, because that's sort of simpler. It's a good place to end because it's kind of simple, but also shows a bunch of stuff that can go on, right? So with homomorphisms, right? Again, this should start seeming really familiar. I've got two rings. Whoops. Two rings, R and S. I've got a map, right, between R and S. And I want the map to preserve operations. So preserve the structure is the usual way of saying this. So it's going to preserve the operations, and phi of 0 has to be 0, right? So that's it. That's what a homomorphism is. Okay. Just like with groups, right? It's exactly the same. You know, for groups, this had to preserve the identity, the additive identity. It had to preserve multiplication and inverses, right? So this is preserving additive, you know, addition, additive inverses, and multiplication, right? If I want my phi to also preserve 1, that's a different set of homomorphisms, right? So if I'm looking at rings with unit, and I want to stay completely inside the world of rings with unit, right? Then I need to also have it preserve 1, right? And if I want it to preserve fields, I need to also have it preserve multiplicative inverses, right? So you can add stuff to your homomorphisms depending on what the official word is category of structures we're looking at, right? So we're looking at right now is just the category of rings. So just all the rings, and which things preserve the ring structure. And the ring structure is like this. It's R0 plus times, and if you like, sort of the minus A, right, where this is the additive inverse, right? That's the ring structure, right? So it's got to preserve those things. And again, the sort of a common example would be phi go from Z to Zn, right? And what is this map? Phi of M equals M mod N. That's a ring, that's a ring. This is a homomorphism, right? How do you show it's a homomorphism? Well, this is exactly an exercise you did back in week 1, right? You're going to show that phi M times K is equal to phi M phi K, right? And what does that actually mean when we unpack it here? It means MK mod N equals M mod N times K mod N, mod N, right? You got to do that extra mod N at the end, because when I take that product, it might be bigger than N again, right? Okay, but we know that, right? We know that from way back at the start of class, right? That's preservation of multiplication, right? Preservation of addition looks the same, right? Pm plus K it is equal to phi M plus phi K, right? Here it's going to look like M plus K mod N is equal to M mod N, whoops, plus K mod N You know, and again, you have to mod in at the end because again, those two things, when I add them together, maybe get bigger than in, right? Let me make that look like something. Right, and then what else do I need to show? I need to show that phi of 0 is 0, right? So this just says phi, well, phi of 0 is 0 mod in, which is just 0, right? There's really nothing to show there, right? That one's kind of for free. Right, so that's kind of a nice, simple example, right? Okay. Then the key example, I'll show you another kind of example that we're going to use a lot, okay? So a very common thing we're going to look at is we're going to look at, we'll look at fields with a variable, right? So these are the polynomial. First, I mean, we look at rings with variables too. This will be really important. Let's just say we're looking at fields with a variable, okay? So among other things, this is a ring, right? And I might want to say, I might want to look at things like this, like phi. In fact, I could do this with R, but I'll just do it with F. Phi going from Fx to F, where what I do is I take phi of the polynomial and I just evaluate it at some element, right? So that's an evaluation function, right? So this evaluation function is a homomorphism, right? So phi of f of x, g of x, right? I want to show, for example, that this is the same as
F and G, F, G.
phi of f of x. And this
and then
product
the F, G of
here,
X.
yeah, this product here, just to be clear, this product is not composition. This product here is just products of polynomials, right? Just to be clear about what that product is, right? So this should be phi of g of x. So let's see if this is true. So on this side, right, I have phi of a, g of a. That's what phi of this is, right? And on this side, I have f of a, g of a, right? So, I mean, there's really nothing to do, right? Phi of the 0 map is just f of x equals 0 for all things, right? Is clearly going to be f of a, which is 0, right? So map 0 to 0, addition, same kind of thing, right?
Dr. K, notation question at the top. You said that's the field of polynomials, right? At the,
Yep. Okay. Yeah. Let me make this clear. So Rx is the set of all. So I'll write it like this: a naught plus a1x plus dot 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 plus a n minus 1. Sorry, a n x to the n. Whoops. Where the AIs are in R, right? So that's the ring of polynomials with coefficients in R, right? So the coefficients are in R,
right.
right? And there's always an assumption here, the usual things, right? AN is not 0, right? The degree of this polynomial, so let me just call this one here P of X, is n, right? Where this is the highest power, right? And the leading coefficient is AN, right? So, you know, however we write that, the leading coefficient of P, you know, is AN, right? Something like that.
Yeah, at the example above that though, you had it being mapped to just F, and I was wondering what it was being mapped to. Is that
Oh, it's being mapped. So I'm taking the polynomial and I'm evaluating it, right?
okay.
So here's a example. Let me give you a real example. So we have QX, and we're going to take the polynomial x squared plus 2, right, is an element of QX. And we're going to look at the ideal. So this is a field, right? I'm going to look at the ideal generated by this. And so that's going to be well, I guess in some sense, I'm kind of jumping ahead here some. So okay, sorry.
Is this where you
This
say
is the stuff we're going
it's-
to do. This is stuff we're going to do next week officially, right? So it's going to be x squared plus 2, basically times q of x, right? So it's going to be all of those polynomials that have a factor of x squared plus 2, right? So all these things that look like x squared plus 2 times h of x for some h, right? So all those polynomials. So you can any polynomial where you can factor out a copy of x plus 2, right? Okay, and it will turn out that this will be the ideal generated by x squared plus 2. Right, and it'll turn out that this is an ideal, so we'll do. Okay, and if you think about this ideal as making things 0, right, that's what you want to think about. So you want to think about x squared plus 2 as becoming 0. Sort of, it's going to be turned into the 0 of this thing, right? So your ideal is sort of becoming 0. So that's like looking at x squared equals. Sorry, let me make this minus 2 to make it a little simpler. It's like saying x squared equals 2, right? Okay. But there is no square root of 2 in the rationals, right? So it's not there, okay? So we'll show that this field is isomorphic to Q adjoins square root of 2, right? And the map that does that will be the this sort of evaluation map going from here over to there, right? Where we're just evaluating at square root of 2. That's what it'll be, right? So we take the map going from qx to q square root of 2 by f of x gets mapped to f of square root of 2, right? And this is a homomorphism. Because it's an evaluation map. We just showed that it's an evaluation map, right? We're using the fact that we know what square root of 2 is, right? So it's a homomorphism. Why is this by the way, why is this this is actually a field. Why is this a field?
That was in chapter 13. I mean, the chapter
this-
before homomorphisms.
Yeah, this is definitely something you teach in algebra. And in fact, I don't know why you teach it in algebra. This has always been a question of mine. Why do we teach this in algebra? Well, because you want them to later use it to prove that this is a field, right? So if I take two things in here and I add them together, do I obviously get a thing in there like that? Right? If I take a plus b squared to 2 and I add c plus d squared, add c plus d squared of 2, right? Then clearly I get a plus c, b plus d, square root of 2,
square
right?
root
So
2.
clearly it's closed under addition, right? Is it closed under multiplication? A plus square root of 2. No, tell me
Yeah,
this
it
isn't
is.
very algebra-like. B,
It is.
c plus square root of 2b, right? Well, what is this? This is going to be a c plus 2, d, b, d, plus square root of 2 times what? A d plus bc. Right? So we took two things inside there and we got something inside there again, right? Okay. So it's closed under multiplication. That's kind of trivial. It's closed under addition. Is it closed under inverses, right? This is sort of the tricky part, right? Is it true that I can compute this and have it be in this form? How do I do that? And what's that called in high school
Rational
algebra?
Conjugate and
the
denominator.
conjugate.
Taking the conjugate of it.
So it's called rationalization, right? And you don't just take the conjugate. You have to multiply up and down by the conjugate.
Yes.
Right, and then it works, right? So on the bottom, what do we get? We get a squared minus 2b squared, and that's never 0 again because remember a and b are in rationals, and 2 can't be, or square root of 2 can't be in the rationals. So this thing will never work out to 0, right? And on the top, we get whatever we get, right? We get a plus b squared to 2, or minus b squared 2. right? So writing it all out, we get a over a squared plus, sorry. Stop it. Minus what, b over,
Isn't that b square root of 2 over? Oh, you took the square root of 2 out. Okay.
yep, square root of 2 is there. Because I need it to be in this form. This is the form c
Yeah.
plus d square root of 2.
That is so dope.
And this is like a question 55 from chapter 14. And if I don't know if y'all look at the discussions, but I did post a link to a video. I just so happened to find a guy who, it was actually one of the guys you suggest we look at. I forgot his
Mhm.
name, but he went through the whole problem. And he kind of talks about ring polynomials and all the things that happen when you're trying to find an inverse of
Yep.
a ideal and with ring polynomials. So anyway,
Yeah, I mean, that's what we're going to do for the rest of the class, essentially, right? So
right.
So in the notes for the rest of the class, I'm basically going to focus on the set of notes that I have, which are called homomorphisms and ideals, I think, right? So that's going to be like the rest of the class is going to be basically on that, but largely it's going to cover dealing with these polynomial rings and their special properties and stuff like that, right? Right, but my point here is that this is a homomorphism because we know this is a field, right? So I'm taking qx and I'm embedding it into q square root of x, square root of 2, using this phi of p of x is equal to p of square root of 2, right? Well, this is a homomorphism. We just showed that a minute ago. What is its kernel? This is another thing you basically teach in algebra. These are polynomials with rational coefficients, right? So in the reals, we know that x minus square root of 2, right? We know that x minus square root of 2 must divide p of x because p of square root of 2 is 0, right? So that means that p of x is equal to x minus square root of 2 times some other q of x, right? But this is not rational, right? So in order for this thing to be rational, what other factor do I have to have in here? You teach this in this form. If p of x is a real polynomial, real coefficients, and x minus like 2i is a root, or in fact, any complex number, but I'll just say 2i is a root. What does another root have to be? Another complex root
x plus 2i.
X plus 2i has to be another root, right? I don't remember what that's called.
Well,
It's called
that's
something.
not real though. That would be a complex number, real root.
No, but
imaginary
the
roots, right?
Yeah, but the point is, real polynomials can have imaginary roots, but if they have imaginary roots, they come in conjugate pairs.
Right.
Okay, so rational polynomials can have square root of 2 as a root, but in order to have square root of 2 as a root, it's got to come in a conjugate pair. So this is another place where understanding this can help with other stuff you actually do teach in high school. The conjugate pair isn't relevant that it's complex numbers. What's relevant about it is that the thing you're factoring out there, you've got Rx over the polynomial ideal x squared plus 1, right? Here we've got Qx over the ideal x squared plus 2. Right, that's sort of the stuff we're heading toward here, right?
Okay.
So the point is, in order for this to have square root of x minus square root of 2 as a root, it's actually got to have both of these as a root, right? And what that means is that px is in the kernel of this evaluation map, if and only if. What is x minus square root of 2 times x plus square root of 2? Well, it's x squared minus 2. Right? So px is in the kernel here. P of x equals x squared minus 2 times some other polynomial, right? But this is exactly the way I defined the ideal generated by x squared minus 2, right? So it's exactly that ideal, right? So the kernel of the map phi there is exactly this ideal. it's clearly onto, right? Anything that I want to write in the form a plus b squared root of 2, I can definitely write that by taking the image of a polynomial, right? Namely a plus bx, right? So it's onto. So this is now jumping into the homomorphism thing. So I've got phi, which is an onto map from qx into q squared root of 2, right? The kernel of phi is equal to the ideal generated by this single polynomial, right? Which is just x squared minus 2 times any other polynomial. Okay. So what does the first isomorphism theorem? It's exactly the same as the first isomorphism theorem for groups, right? It's going to tell me that this image, right, m phi, which is q squared root of 2, is isomorphic to qx, that's the domain here, modded out by the kernel. Right? So this is going to tell me that q squared root of 2 is isomorphic to qx modded out by x squared minus 2. Okay. So what we're going to do in a large part of the class is, at least mainly in the last 2 weeks, if you like. I mean, there is a exam in that last week too. But we're going to look at adding roots to polynomials that don't have roots, right? And so R is the same thing, right? R square root of minus 1 is isomorphic to Rx over the ideal generated by that polynomial, right? Because basically we're throwing in x squared plus 1 has to be 0, right? Because remember, this is going to become the 0 of whatever that thing is, right? And then we're going to deal with more general things, like you have a polynomial that doesn't have a root, right? You want to add a root to it. How do you add a root? Well, you do some construction exactly like this, using these fields of polynomials and stuff, right? So this is just, so in the end, this will lead up just to the very edge of what's called Galois theory, which
Spell that.
we won't
Can you
quite
spell
get
that?
to. Galois, yeah. I mean, I've got a link in there too. I think right at the top of the class, because there's some cute videos on Galois. I mean, the guy invented this when he was, I don't know, 19, and he wrote it down the night he died in a duel, and it's a great story, right? He was active in the French Revolution, and really worth sort of getting to the history a little bit there. Okay, so we made it, I don't know, largely into chapter 14 and 15. Give it a shot. Good. Any last minute questions?
Will
my-
the final, go ahead, Dina.
Oh, my question that I had earlier actually was on, what was that we were talking about? Gaussian integers, exactly. So I will check out your video and see if I can get an answer there.
There's also a whole one of the, on the extra notes, I have a whole set of extra notes on just Gaussian integers. So it's a big field, and it's worth going to YouTube and just looking up some videos on Gaussian integers too, as a really useful stuff actually. And a lot of really interesting number theory, like what are the primes in Gaussian integers is really interesting, right? So it gets down to questions like, when can you write a prime in the form c squared plus d squared, right? Where this is prime and these are integers, right? So you get into interesting number theory that sort of has to get involved. That's the reason it's not an easy question to answer. It requires a little bit of effort to answer that question. And what was the other question?
My question, Dr. K, was, will the final be over everything we've learned over 8 weeks, or just what we're learning from now until the end?
I mean, it'll be from what we're learning from now to the end, but everything we do now to the end, definitely, I mean, so there is some group theory stuff that we won't see again. We won't see, like, I don't know. I mean, but you still need to know what groups, I mean, because rings, fields, etc., they involve groups, right? So so like an example that's also in the notes is, what are the homomorphisms, say, between Z12? This is a good question to think about. Like, think about what are the homomorphisms between Z12 and say Z28 or something, right? Ring homomorphisms, right? And there's actually two things you have to think about. You have to, because you know that it's going to completely depend on where phi of 1 goes, right? So on the group side, what you should know now is that in order for this to be a group homomorphism, 28 has to divide phi 1 times 12, whatever you multiply that to, right? So that's sort of on the group side of things. So we're looking at what group homomorphisms are there between these two structures, right? But then on the ring side, we need to know that phi of 1 squared equals 1, right? So that's a new kind of thing that we need to check, right? And then those two conditions together tell you what kind of homomorphisms you can have, right? So that's a situation where you still need to know a fair amount of group theory together with the new stuff.
So the GCD and the square root stuff is still all valid. Because that kind of looked like another way for you to write. And I'm just thinking out loud, Dr. K, I'm
Yeah.
sorry.
That's all right.
I'll probably, tomorrow morning, I have a break from 8 a.m. until 9:30 a.m. my time. I'm not sure what time that is your time. I think it's too early for me to bother you. I think it's like 6 a.m. That's why I haven't been able to schedule meetings with you, because that's my planning period this year, this semester. So it's like I work until it's to like 7 o'clock at night my time, which is 5 o'clock your time, which is late. So I do have some questions, but I guess what I'm gonna try to do is figure out at the end of the week.
I mean,
Just
I
catch
do
up on
have,
some.
so I have given you a way of signing up with scheduling appointments with me, and there are
No,
some
I-
available at 5 my time. So that's a possibility.
No, but that's what I'm saying. My days are packed until like 9 o'clock at night. It's literally everything is packed. But I do have a fall break coming up this week. And even though it's stuff that's passed, I'm probably going to ask questions about stuff just to make sure that I have a strong enough foundation to move forward and schedule something with you either Thursday or Friday. That's all I'm saying, is giving you a heads up.
Okay, that's fine. Yeah.
Thank you.
Anyone can
Yeah,
schedule with me. Yeah.
Yeah, have
Any
a
other
good evening.
questions?
This will be posted, right, Dr. K? This video?
So someone else has asked for it. So remind me I mean, I can't do it right now because it's got to
I know.
settle and I've got to upload it, and but remind me if it's not up by tomorrow night, for example.
All right. Thank you.
Mhm.
Good night, everyone.
Any questions from others? Nope. Okay. Nope. Okay. See you later. Bye-bye.